Good morning, everyone. Are you able to hear me properly? Can someone confirm to me that you can hear me? Hello, can you hear me? Okay, all right. Thank you. Okay, good morning. Welcome to our lecture, our fourth lecture on complex numbers, and we are continuing with the polar form. If you have any questions, please feel free to post them in the chat and then I will attend to them as I am going. Okay, so we know that a complex number can be written in standard form, and now we've got the polar form where we say z is equal to r times cos theta plus I sine theta, where the real part is r cos theta and then the imaginary part is r sine theta, and r is just the modulus of z. And we also have the principal argument, which is between minus pi and pi. And so we want to be able to, there's a general question that we want to answer, which is if you're given a complex number like this, for example, and then you want to find that to the power 2023 or some big number, are we able to do it quickly? And today we will be able to develop the theory to be able to do it. And so we said if you've got two complex numbers, z and w, then when you multiply them, you can see that if you multiply them, then the r becomes just the product of the two here, and then the angle or the principal argument, maybe not the principal argument, but the argument becomes theta 1 plus theta 2. You might have to adjust it to be within the specified interval, but otherwise it's theta 1 plus theta 2. And then we have that. So now we go on to the theorem that helps us to answer this question, to be able to calculate this quickly, relatively quickly. Maybe not quickly, but relatively quickly. And this is De Moivre's theorem, theorem 6.3.9 in the textbook. And it says if you've got a complex number z, which you can write in polar form, and if n is an integer, here we are going to prove the natural one, the positive one, but otherwise the full theorem is when n is an integer. So this is not the full theorem. We are just going to prove this one, and then you can do the other part as an exercise. So if n is a natural number there, then z to the n is going to be equal to r to the n, and then cos n theta plus I sine n theta. right? So the problem reduces to, if you find the modulus, now you can just take the power of some number, which is relatively easy to work with, and then you also multiply inside there by n, and you can then still get the principal argument, and then you've got the z to the power n. So it sort of makes it easier. Not sort of, it makes it easier relative to naively working on this directly, right? So that is it. So that's the theorem. It tells us how to get powers of complex numbers, and it makes the calculation easier. There's a question which says, just to be sure, you're excluding minus pi in the argument, right? Yes. So yes, minus pi is not part of the set or part of the interval that we are looking at. So for example, I think yesterday we had, if you get minus pi, for example, you have to add 2 pi because it's not within, and then you get pi for you to be able to get the principal argument. So minus pi is out and pi is in the interval. Right, so let's look at the proof. So I said the full theorem says n is an integer, but we are going to look at n being a natural number. And then you can do the other one as an exercise. So let's look at the proof. So the proof is, our strategy is the principle of mathematical induction. That's what we are using. So we start off with the basis step or base step, whatever appropriate language is used, but all of it is fine. It just depends on the text. I'm sure the textbook uses basis step. Right, so what we want is to check, is it true for n is equal to 1? So the question is it true for n is equal to 1? That's what we want to check first, right? So that's your aside there. That's what you want to figure out. So if I look at z to the 1, right, that will be the left-hand side here. So the left-hand side is going to be equal to z to the 1, which is equal to z, which by definition of our complex number is just r cos theta plus I sine theta, right? That's the first thing. And then if we look at the right-hand side of our statement, it should be, so it will be r to the 1, right? Because n is equal to 1. And then it is times cos times 1 theta plus I sine 1 theta, which is equal to, so r to the 1, we know it's equal to r, and then cos 1 times theta is theta, plus I sine 1 times theta is theta there, so we get that, and we can see that these two are equal. So in other words, so the left-hand side is equal to the right-hand side, and so our result holds for n is equal to 1. Right, so that is, so we know that the statement, it is indeed true for n is equal to 1. Now we go on to the induction step, or the inductive step, right? So induction step. So we start off with the assumption. So the inductive assumption. So we first assume that the result is true for n equal to k. But what does that mean? That means that we are saying assume that z to the k is equal to r to the k cos k theta plus I sine k theta, like that, for some k, right? Now we want to check if it is going to be if it is going to be true for n is equal to k plus 1. So what do we want to do? We want to show that the result holds or is true for n is equal to k plus 1. In other words, we want to show that z to the k plus 1 is equal to r to the k plus 1 cos k plus 1 theta plus I sine k plus 1 theta, like that, right? And then so our strategy would be to start maybe with z to the k plus 1 and hopefully end up with this on the other side, right? So, and we want to use this inductive assumption. Let me just call it inductive assumption here. We are allowed to use it, and then we are allowed to use any other things that we already know about complex numbers, right? And even about cos and sine. So we start off with z to the k plus 1, and we know that this is going to be equal to z to the k times z, right? This is pretty standard. And then from here, what is z to the k? Z to the k, from our inductive assumption, we can say this is going to be equal to r to the k times cos k theta plus I sine k theta, right, times z, and z is equal to z is equal to r cos theta plus I sine theta, right, like that. And here we can say this is because of the inductive assumption. So that's what we used. Here we just substituted what z is equal to. Maybe let me put brackets there. So inductive assumption there. So here we just substituted, and here we used the inductive assumption to get that. And then from here we then say this is equal to r to the k plus 1, right? If we multiply that r to the k with that r, we get r to the k plus 1. And then when we multiply these two, theorem 6.3.6 tells us how to do that. Where is it? It's here, right? It tells us how to multiply two complex numbers. And so we get r to the k plus 1 and then cos k theta plus theta, right? Plus I sine k theta plus theta. And this is coming from, as I've mentioned, theorem 6.3.6. That's what tells us that. And then from here we can then say this is r to the k plus 1 cos, and then we can factor out our theta there. We get k plus 1 theta plus I sine. There we also factor out theta. We get k plus 1 theta, like that. And then we get that. And if we look at what we now have here and what we wanted to get, we can see that it's the same. So therefore, it means that so result holds, or result is true for n is equal to k plus 1. And so therefore, by the principle So by the principle of mathematical induction, our statement is true, right? So that is the proof there. So here, remember I mentioned that here we just proved it for natural numbers. That's why we can use induction. But the statement is actually true for any integer that you pick, right? So if you look at exercise 6.3, number 5 in the textbook, it will ask you to do the full proof by looking at the negative values that you have. Again, you use induction, you just have to make sure that when you're dealing with the negatives, you just deal with those ones. But otherwise, it's still induction, or at least maybe not even induction. You just need this, what we have proved here for natural numbers, and then if you take them, the negative values, you should be able to connect to what we have done here and then get your answer. Right. So we proved that it's true for positive integers, and then look at exercise 6.3 number 5 to do the rest of the solution. Right, now let's see what this implies in terms of getting powers of complex numbers. Right, so so we've got an example here. Let z be equal to 2 minus 2i, and you want to be able to find z to the 8 in standard form, and z to the minus 4 in standard form, z to the 7 in standard form. And so how do we deal with this? So we want to use De Moivre's theorem to be able to do this. So the first thing is we want to change the form that we have. There we are given standard form. For us to be able to use the theorem, we want to write our complex number in polar form. Then we are able to use it, right? So let's see. So the first thing is to find r, which we know is the modulus of z, and in this case it's just going to be equal to the square root of 2 squared plus minus 2 squared, which is 4 plus 4, which is 8, so it is square root of 8, like that. And then to find theta, you can just say, well, there are several ways of doing it. You can say the arctan of minus 1, because if you look at that ratio, it's just going to be minus 1, and then you get pi over 4, and then minus pi over 4. Just a tip. So one advantage of using the interval minus pi to pi is that whatever the sign that we have here is what is going to be the sign on the argument that you're going to get. So for example, here, if I say, okay, let's do it the sort of long way, where you say 2 minus 2i is equal to square root of 8 cos theta plus I sine theta. Here we just want to find what is theta, and then you say, if I take the real parts, then I've got 2 is going to be equal to the square root of 8 cos theta, and then if I take the imaginary part, I get minus 2 square root of 8 sine theta, and then if I find my cos theta, I'll see that cos theta is just 2 over the square root of 8, which is, if you write the square root of 8, you can write it as 2 root 2, right? And that cancels, so you're left with 1 over root 2. And so the arc sine is going to be, arc cos, so theta is going to be pi over 4 or minus pi over 4, right? Because cos is positive in the first, remember, all STC, so cos is positive in here and in the fourth quadrant, so we get these two angles. And for you to figure out which one is the right one, then now you want where sine is negative, so you then say, but my sine theta is also minus 2, or let me just write it right away, since we know what the expression is the same, it just says a negative sign there. So we get minus 1 over root 2, and we know that sine is positive in here and in there, so it has to be negative either in here or in there. But this one is the one which satisfies both expressions there, so therefore it is in the last one there. So therefore we can say theta is equal to minus pi over 4. So my point was, whatever the sign here is, it is going to be the sign on the angle, and we can see there that this one is also negative. So we've got a negative imaginary part, right? Something less than 0, and we also have a negative argument. So that's always the case. So that's one advantage of using this interval. Sorry, here it's closed and then the other side is open, right? So we know that our angle is that, and so therefore what we are saying is the square root of 2 is going to be equal to, sorry, not the square root of 2, z can be written as the square root of 8 times cos minus pi over 4 plus I sine minus pi over 4, right? And then from here, now that we've got z, we can now find all these z to the 8, z to the minus 4, z to the 7 by using De Moivre's theorem. So we say z to the 8 is going to be equal to the square root of 8 to the power 8 times cos n theta, so 8 times minus pi over 4 plus I sine 8 times minus pi over 4, right? And then from here, we can then say, but this is just, so if I find this, this is just 8 to the 4, right? Because square root, you can say 8 to the half times 8, you get 8 to the 4. And then here you get cos of minus 2 pi plus I sine minus 2 pi, like that. And then from here you can then say, let me add a page here. You can then say, okay, I'm just going to continue here. Maybe let me just squeeze it here. So here we can then say, let's, so if you look at minus 2 pi, it is not in the interval that we want. We want to, we want the principal argument. So we would say, because it's too small, we have to add 2 pi. So we get 8 to the 4 plus, if we add 2 pi, we get cos 0 plus I sine 0. And then from here, we can see that this is just 8 to the 4, cos 0 is 1, and then sine 0 is 0, so we get this. So it's already in standard form there. And then we get our answer in standard form, right? So if it was not, then you will have to, suppose it was some different angle or different argument, then you have to find what the the cos of that is and what is the sine, and then you write it in standard form like that. So that is that. So that's how we look at these problems. So you can look at the other the other parts as homework. So B and C is homework. You can go and look at them and then see how to do them. That should be easy enough. Now that we've got De Moivre's theorem, we can use it. Right. So let's look at another example, which deals with how to draw sets using modulus and argument if you're given that. Right. So I hope this shows you, or it's clear how we can use De Moivre's theorem to be able to find these powers. If you have questions, feel free to post them in the chat. Right. So I'm going to look at examples. So the example is exercise 6.3, and that is number 2 in the textbook, and it says you're given A, which is a set of all points okay, let me just write it the way it's written. So A is the set of all complex numbers, set of all complex numbers Z with principal argument principal argument theta, which is between pi over 4 and 5 pi over 6, such that the modulus is between -2 and 2. So here, so we can write this in set form. This is the set of all complex numbers that satisfy this. So the argument of Z is going to be, oh, maybe let me write it in as an inequality. Pi over 4 is less than or equal to the argument of Z, which is less than or equal to 5 pi over 6. And the other condition is the modulus is between that. So that's the set that we want to draw on the complex plane, right? So we want to sketch A. So let's see what we have. So we've got the real x is there, the imaginary x is there, and then we want to draw this region that we are given, this set of complex number. So what we do is the modulus, so we want to figure out what kind of points have this are between this and that. So what we do is we have to draw a circle, right? So that is the first one. So any complex number with modulus 1 is going to be on this line. Maybe let me draw it as a dotted line. Well, it's equal, less than or equal to, so I think a bold one is fine. Okay, so we've got that. And then, so here we will have I, there you've got 1, there you've got minus I, there you've got 1. Those are your points. And then, maybe let me extend this. Like that. And then maybe 2 is here, so we say 2i there, and then we draw another circle. So the complex numbers such that the modulus is between 1 and 2 should be within the donut there, right? So we are talking about points in between here. And then now the argument tells us something. So the angle is between pi over 4. So if I draw it roughly there, it will be pi over 4, and then 5 pi over 6. So this actually extends to that, right? Those will be all the complex numbers whose argument is pi over 4, and then 5 pi over 6, I think, should be in the second quadrant there somewhere. And then, so it will be going up in those directions. So the region that we want is when the the modulus is from 1 to 2. So 1 to 2, we know it's in the donut, and then whose argument is between pi over 4 and that. So we want everything that is, if we think about, so maybe let me use two different colors to just illustrate what we are talking about. So for the modulus, we want all the points that are here, right? So those are the points that have modulus between 1 and 2. And then for the argument to be between pi over 4 and 5 over 6, let me use red. Then we are talking about all the complex numbers. So this whole region there, right? We are going in that. And as usual, because we want a region that satisfies both, we are going to take where they intersect, and you can see that the way they intersect is from here going there, and let me use black. From here going there, so anything in between these is going to be the region that we want. So we can draw another little sketch there. So we've got 1 there, we've got 2, and then that. So we are talking about this region over there. This is what is A. You can label 1, 2. You can label minus I, minus 2I. This is minus 1, minus 2. This is I, and this is minus 2I on this point. And you've got your imaginary axis there, you've got your real axis there. So the region that is shaded there is the region that we want. Right, so that's how you sort of look at this type of questions in case you meet some questions like that. Right, so let's move on to the next thing that we have, and it is chapter 6.4, and we are looking at the complex exponential. Right, so our first question that we ask is, well, we sort of have, so as you saw that whenever we are dealing with complex numbers, since they are an extension of real numbers, we sort of want to explore all things that are real, that we know about real numbers, and then we see what happens if you are dealing with a complex number instead of a real number. So in this case, we know the exponential, which is fundamental in maths. We have seen it come in different shapes and forms. And the question is, can we also define e to the z, where z is a complex number, right? And the answer here is yes, we can. And so for the most part, we'll just be looking at how to deal with these new objects that we have, e to the complex number. So how do we define it? So if you've got a complex number z, which is a plus bi or a plus ib, where a and b are real numbers, then e to the z, right, is going to be equal to e to the a times cos b plus I sine b. So basically, you're going to have the real part there, e to the real part, and then cos to the imaginary part, cos b plus I sine b I, like that. And we can check if it's going to be consistent when we are dealing with real numbers, our new definition. So if you've got z, which is a plus bi, and if it's a real number, well, which means that b, the imaginary part, is equal to 0, then e to the z, we expect it to just be e to the a, right? So if we substitute into this new definition that we have, we are going to say e to the a times cos of 0 plus I sine of 0. So if you look at cos of 0, it is going to be equal to 1. And then sine of 0 is going to be equal to 0. So this disappears there. And then you're left with e to the a, which is what we expected if you're just dealing with real numbers. So it is consistent. Now let's look at a simple example to just see how it works. And this is, so suppose you want to find e to the z, where z is equal to that. Then you are going to say, well, this is my real part, this is my imaginary part. So I know that I have to say e to the half of the natural log of 2, right, which is the real part, times cos of the imaginary part. The imaginary part is pi over 4 in this case, like that, plus I sine pi over 4. And from here we can then say, but this is just equal to e to the, if we use our laws of logarithms, we know that this is e to the natural log of 2 to the half, right, or the square root of 2, times cos pi over 4 plus I sine pi over 4, like that, right? And from here we can then say, what is e to the natural log of 2 to the half? That is just going to be equal to 2 to the half, which is the square root of 2. And then if we find the cos of pi over 4, it is, we know that is square root of 2 over 2 plus I sine over 4, which is equal to root 2 over 2, again the same. And then we can then rewrite that as 1 plus I. If we multiply throughout but by the square root of 2, we see that square root of 2 times square root of 2, we get 2. So 2 over 2 is 1, so we get 1 plus I. And that will be e to the z in standard form. Right. So that is what we have there. So if you're given a question like this, I'm sure you are able to look at it. Now let's look at some properties of exponents that we know in real numbers that we want to check if they are going to be true in complex numbers. So, and this is theorem 6.4.3 in the textbook, and it says, if z and w are complex numbers and n is an integer, then e to the z times e to the w is going to be equal to e to the z plus w, which is what we would expect if you're dealing with numbers, real numbers, and you've got x, e to the y, you expect e to be equal to x plus y, right? That's what we know. And then also with exponents, powers there, we can say e to the z to the n. Well, if you're dealing with real numbers, we know this is e to the xy, right? So this can be extended to complex numbers. And for the proof, you just need to use the definition that we are given to be able to do the product. So for example, if we take z to be equal to a plus bi and w to be c plus di, then all you need to do is e to the z is going to be equal to, so e to the z times e to the w is going to be equal to e to the a plus bi, which is e to the a times cos b plus I sine b, and then e to the w would be e to the c times cos d plus I sine d, like that. And then you apply what you already know, e to the a times e to the c for real numbers. This is true, so that's fine. And then there you just then say this is cos b plus d plus I sine b plus d, right? If we use theorem 6.3.6, and then if you look at e to the z plus w, you see that that is just the same as that, and so therefore you would have shown that they're equal. So you just need to now find, well, you can write z plus w here, which is a plus c plus b plus di, right? So if you then calculate a to the z plus w, then you get the same expression there, and that will be the end of the proof. So you can also do this one for yourself, so leave it as an exercise. Right, and now we go on to something that is fundamental in maths, that is Euler's identity. So, and one of the things that it does is it tells us how, it gives us an equation which includes some fundamental things that we know in maths. Let me add a page somewhere here. Maybe let me put it there. Right, so so the constants, we've got 0, and we know what 0 does. If you say 0 to the 0 plus x, we get x, right, for some real numbers. And 1, so this is our additive inverse. This is our so let me say math constants this side. So 5 math constants that we know. So this is an additive inverse for real numbers. We know 1 is a multiplicative inverse, so 1 times x is equal to x. So that's very important to us. And pi, we know, for example, that the area of a circle is pi r squared. And if we think about e, so all these are special to us. If you think about the derivative of e to the x, it is equal to e to the x. That's a special thing. Or if you think about a to the natural log of a, it is going to be equal to a. Or if you think about the natural log of e is equal to 1. So all these things are special. So these numbers are special in that way. And then we've got this new kid on the block. I squared is equal to -1, or I is equal to the square root of -1, which is pretty special for us. And we've got this result, Euler's identity, which has all these things. And it says e to the power pi I plus 1 is equal to 0, which is pretty remarkable to have all these in one statement, which is a true statement. So in case you don't know Euler, you can Google him. He was a very prolific mathematician. And there's a lot about him. Right, so let's see how we can prove this to be true. So if we say e to the theta I, which can be written as e to the 0 plus theta I, if we're writing it in polar form, sorry, in standard form, this would just be equal to e to the 0 times cos theta plus I sine theta, right? By the definition that we are given. And then this is going to be equal to cos theta plus I sine theta. So if we say e to the pi I plus 1, what we are saying is this is cos, if we just follow that, cos pi plus I sine pi plus 1. And we know that cos pi is equal to minus 1 plus this sine pi is 0, so we've got 0 plus 1, and then we get that to be equal to 0. So the identity is indeed true by that simple calculation. So one thing I didn't mention, which I think is important, is the fact that when we introduce the complex exponential, we end up being able to write a complex number in terms of this new polar form. So it's still a polar form. So if you know your r and your theta, then so if z is equal to r cos theta plus I sine theta, then it means that we can write this in shorthand by saying this is going to be equal to r e to the theta I, like that. So that becomes a shorthand polar form that we can use when we are dealing with the polar form of a complex number, right? So that's a new format there, which is shorthand. All right. Let me look at another example before we stop, and that's exercise 6.4, number 3. And it is asking you to be able to write complex numbers in this new form, new polar form, r e to the theta I. And so what you do is, so if you're given, for example, 1 minus I as your complex number, then you want to find its modulus, which is root 2, and then its theta is minus pi over 4. We now know how to do this. You can find the theta pretty easily, and again, remember that the sign there would be the same as the sign there. So therefore, 1 minus I can be written as the square root of 2, which is our r, and then e times theta I, and in this case, theta is minus pi over 4I, like that. And that is our complex number in polar form, r e to the theta I. And in the normal form, we then say this is the square root of 2 cos minus pi over 4 plus I sine minus pi over 4 in the normal one that we have. So these will be the two forms, even though the question just wanted this one, right? But it's pretty much the same. If you think about minus I, again, you're going to say the modulus is 1, right? And then the theta is going to be equal to minus pi over 2. This you can easily see if you draw the argand plane and then you put minus I, you see that minus I is somewhere here. So if you look at the angle there, it will be minus pi over 2. And so again, you do the same. Now that we've got the modulus and the theta, you can write it as minus I being equal to 1 times e to the minus pi over 2I. And that's how you write it in polar form, the shorthand polar form. And that's that. Right. So that's how you tackle those type of questions. And I'm going to do this one as the last one before we stop. And so we want to plot a set in the complex plane of a set that we are given the set in exponential polar form, right? And that we want to draw this. So it's pretty much the same as what we did previously. So we know R is between 2 and 3. So just think of the modulus. You're going to say 2 there, 2I, 2 minus 2I, and then you've got 3, sorry, minus 2 there, right? And then you draw another circle, right? And that will be 3I minus 3I and 3 there. So that is the region. And then if we draw the angles, they will look something like that. That's pi over 4. That's pi over 4 there. And so the region that we want is going to be this region. Because that is the region that satisfies both cases. And in this case, you should have dotted lines, because if you look at that, those are strict inequalities, right? So you shouldn't have the boundaries because of this and that and that and that. And that is it for today. Thank you for attending. If you have questions, feel free to stay behind. Otherwise, enjoy the rest of the day and the weekend. I'll be here for a minute or so to answer any questions. Thank you. Bye. Okay, it seems there are no questions, so thank you. Enjoy the rest of your day. And we meet on Monday, where we start chapter 6.5. Thank you.